Okay, so I'm going to start the recording now, and remember that I'll, instead of posting the link to Zoom, I'm going to start posting the recordings on YouTube. So I'm going to be sending a link to YouTube, and that's going to have the recording. Unfortunately, making it offline, the files are too big, so I can't send them. They're 120 megabytes or something like that. So they're a little too big. Yeah, so if you want to write your name into the chat now is a great time to do that, because we are recording, so your name will be recorded in the chat if you want to go write it in. Okay. All right, so why don't we get started? All right, I hope everybody
Hi,
had a good week. Hi, Tomas, how are you?
Fine, thank you.
Good. Okay, so I'm gonna mute everybody for now, just so that everybody can hear. So I'll give a quick mute. Okay, so let's start like usual with going over the homework. So if you remember on the homework, there was one bearings question, and then after that, a couple of matrix questions. And for the rest of today, we're gonna learn a little bit more about matrices. And then next week, we're gonna talk about the interaction with matrices and vectors. Okay, so let's start with the homework problem 1, which we solved part of. We solved part of this problem last time, but there's one more part of it that was on the homework. So suppose we have 3 ships, A, B, and C, and then we have this information. The bearing of C from A is 135. The bearing of A from B is 45. And then we also know these distances. So if A is 8 kilometers from B and A is 6 kilometers from C, then the question is, what is the bearing of B from C? And last time we asked what the distance was from B to C, and we found out that that was 10 kilometers. So what we had last time, I'm just going to draw the diagram. We have A over here, and I'm always going to draw the north-facing line from everything. And then the bearing of A from B was 45. So B was over here. This was B, and this is the line from A to B. And then the bearing of A from C was 135. So we wrote that C maybe over here, like this. This is C. And then we drew a line from B to C. And if you remember what we did last time, we showed that this here was a right angle. The angle at the triangle angle at A was a right angle, and we could label all the sides of the triangle. This had a distance of 8. This was a distance of 6. And because it was a right angle, we used the Pythagoras theorem to show that the distance from B to C was 10. Okay. So this is all stuff that we did last time. Okay, so the question here is we want to know what is the bearing of B from C, right? So we want to know what's the bearing of B from C. Okay, or equivalently, if we figure out what the bearing of C from B is, then that's good enough to do everything. And let me just label some angles so we remember what this looks like. So this angle here was 135 degrees. And this angle here was 45 degrees. And so what we really want to find out, for instance, if we want to figure out the bearing of B from C or the bearing of C from B, one way of doing it would be to figure out what this angle is over here. Okay. So does anybody want to start things off, talk about how you solve this problem or an idea to start solving this problem? Figure out the bearing of B from C.
Yeah.
Yep. Tomas?
Okay. I would like you to show the last diagram. At least from there, we'll be able to. If it's not able,
so the last diagram. So let me see from the old notes. So let's see what we have over here in the last diagram. Let me go back. This one or the next one?
Yes, that one.
This one?
No, the next
Oh,
one. The
this,
other
No,
one.
no,
this
no,
one.
no.
This one.
Yes.
Yeah.
Okay. So
Okay,
what
from
do we do?
C, from yeah, the angle in C. Let's go in C.
Mhm. So the angle that goes from C.
Okay, the angle in C is divided in two. One
Right. So
is
this angle over
45,
here, right?
another angle, yeah.
Mhm.
One is 45, and another one I call theta.
Okay, right. So this here is 45 because of alternate interior angles. And this one here is theta.
No, 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 no. Inside the angle in C, angle ACB.
Angle ACB, right? That's theta.
Yeah, angle ACB, one is 45 and theta is another angle. There are two
Okay.
angles there.
Okay, so sorry, you want me to label theta is, sorry, you want me to label theta as this angle or as this angle? The first one or the second one?
No, the first one, angle
The first one, right, okay.
ACB.
So I'm labeled ACB, right? So this angle theta, right?
Okay.
Yeah.
Yeah, it's divided in two. There we have 45 on theta. They're not only theta, they're 45 theta.
Right. So here we have, right, so we've got 45 and we've got theta, right?
Where you put on theta, there is not only on theta, 45 theta.
Okay, so you want me to divide this up into a 45-degree angle and a theta angle?
Okay, okay.
Well, okay, but I don't know where to draw a 45-degree angle here. Oh, I see. You want I see. You want this to be, I see. So you want this to be, I see. So this diagram's not so good. I see. You want 45 degrees. You want this to be divided so that we have a horizontal line, and this gives you 45 degrees up here, and then the rest of the angle is theta?
Yes.
Yes. So let's do it on the new diagram, which is a little better than the old diagram.
Yes.
So why not we do it like this? So this is 45, and then I'm going to draw a little horizontal thing over here, right? So this is also 45, and then this teeny angle right here is going to be theta. This is what you want.
Okay. Yes, yes. Thank you.
Good.
Thank you very much.
Good.
Okay. Besides that, in B,
Mm-hmm.
the angle in B, there you will see. I gave the another angle. I call it beta or alpha.
Okay. So this angle should be, let me use a different color. So this angle here should be alpha.
Okay.
Yeah.
Okay.
Mm-hmm.
So this angle will before the bearing of
alpha,
B
and we
C
have theta.
will be, yes. So the bearing of B from C will be 180 plus 90 minus theta.
Great. So the bearing of B from C is exactly, what do we have here, right? We have 180 to go all the way down, to go all the way around here is 180. And then if we went all the way up to this horizontal line, we would have 270, but we're not going all the way up there. So we only have theta. So I agree. It's 180 plus 90 minus theta. Yep.
Okay. So we are going to find theta now, but before theta, we find alpha first.
Okay. So let's find alpha. Good. And so how do we use trigonometry to find alpha?
Yes.
So
I use trigonometry to find
Right. So you can use any trigonometric function you want. So which one did you use? You can use sine or cosine or tangent. Use tangent.
I use tangent.
Okay, so tangent of alpha is going to be
Yeah,
equal
I
to
use
what?
tangent.
Yeah. So tangent of alpha equals what?
6/8.
Exactly, right? It's 6/8 because it's the opposite over the adjacent.
Yeah.
Okay, so arctan
Yeah.
6/8.
So yeah.
And so what is
So
the
alpha
so
hello?
alpha is how many degrees?
Okay, alpha will be the inverse of tangent between 6/8 equal 37 degrees.
Okay, so alpha equals tan inverse of 6/8, which is roughly, let's call it 37 degrees. Great.
Yeah.
So alpha's 37 degrees,
So,
and what does that tell you?
From there, okay, the next step, I'm going to find out theta. So I will say alpha plus 90 degree plus 45 degree plus theta equal 180.
Exactly, right? Because all the angles in the triangle have to add up to 180. So alpha plus theta plus 45 plus 90 is equal to 180, right? Because we're adding up all the angles in the triangle.
Yeah.
Good. And so, well, we know this is 37 degrees. So theta equals, let me just, we can finish this up. So 180 minus 90.
Degree.
Exactly, minus 45 minus 37, which is roughly 8 degrees. Good. And so then what's the last step now that we know that theta is 8 degrees? So now that we know theta is 8 degrees,
the bearing. Yes, I just to find the bearing of B from C. I just add alpha to theta plus 90 degree for 60 equal 360.
right. Well, we already have an equation though, right? We already figured out that the bearing of B from C is 180 plus 90 minus theta. Right? So we can just plug theta in right to here. We don't need to do anything more, right? So in this case, it's just going to be 180 plus 90 minus 8, and that's going to be 262. 262, which is going to be the correct bearing. And there's lots of ways to do this. There's lots of different correct ways to do this, right? You could use tan, you could use sine, you could use cosine. Instead of worrying about, you could instead decide that you wanted to figure out the bearing of C from B, which is just going to be 45 plus alpha. So then once you figure out alpha, you know 45 plus alpha, that's the bearing of C from B. And then once you know the bearing of C from B, you know that you can add 180, and that's going to give you the bearing of B from C. So there's lots of different ways of solving this problem. Okay, but yeah, the correct answer, and this is a very nice solution. And so the correct answer here is 262, or 260, going to be 262.1 if you want more precision. Okay, so yeah, so this is a pretty complicated bearing problem. I don't think you're going to get anything more complicated than this. But as all that you have to do is just remember to draw your triangles and draw as many lines as you can. And whatever angle you need, you can always write it by breaking it up into pieces. So like here, we wanted this whole angle, and we could break it up into 90 degrees and another 90 degrees and another 90 degrees, but that overcounts by theta. And so then you just have to figure out what the theta is. So yeah, so this is a really excellent solution. So thank you, Thomas. Okay, are there any questions on this?
No, it's okay.
Okay, anybody else? Okay, so let's talk about problem 2. Problem 2 is much more basic, so maybe I'll just go over this to save some time. So we're given two matrices here. We want to calculate A minus 2B and 3A minus B. So, I'm just going to do these out because this is pretty straightforward. So A minus 2B is equal to 1351 minus 2 times 1410. And that's equal to 1351 minus 2820. Because remember, we multiply the 2 by everything. We just multiply it by every entry in the matrix. And so this is, in the end, you just have to subtract every entry from its corresponding entry in the other matrix. So this just gives us 1 minus 2 is minus 1. 3 minus 8 is minus 5. 5 minus 2 is 3. And 1 minus 0 is 1. So this is the answer for the first part. Right. So this should be relatively straightforward. Any questions here? Rufus, do you have your hand raised?
Yes, but Andrew, please.
Yes.
Yeah.
Princeton.
Please help me and go back over the problem. I beg you.
Over the matrix?
Yeah, starting from A minus 2B. Start from there, go back, please.
Sure. So A is this matrix, so I just wrote it down. And then B is this matrix, so I'm just multiplying it by 2. Right? So the first thing that I do is I multiply 2 by the matrix. How do you multiply a matrix by a number? Well, you do that by multiplying every entry in the matrix by that number. So it's the same thing that you do for multiplying a vector by a number. Right? If I multiply a vector by a number, I take every entry in the vector and I multiply by that number. So same thing for a matrix. So the first thing that I do is instead of 2 times 1410, I multiply everything by the 2. And so this becomes 2820. Right? And so now I have 1351 minus 2820. And then to get each entry in the matrix, I just subtract the corresponding entries. So if I want my upper right and my upper left entry, that's 1 minus 2. That's going to give me minus 1. And if I want my upper right entry, that's 3 minus 8. That's going to give me minus 5. And if I want my my lower left entry, that's 5 minus 2. That's going to get me 3. And if I want my lower right entry, that's going to be 1 minus 0, and that's going to give me 1. So that's how I get all of these different entries. Is that okay?
Yeah. Thank you.
Okay.
Yeah.
Great. You're welcome. Okay, great. So let's just do the other one, which is the same. So if we want 3A minus B, this is 3 times 1351 minus 1410. And we multiply the 3 by everything over here. So that's going to give us 3, 9, 15, 3 minus 1410. Right? Because I multiply every entry here by 3. That's getting me 3, 9, 15, and 3. And then I just do the subtraction. So 3 minus 1 is 2, and 9 minus 4 is 5, and 15 minus 1 is 14, and 3 minus 0 is 3. Right, so this is going to be the answer for the second part. Okay. All right, any questions on this?
No, it's okay, sir. Thank you.
It's okay. Okay, great. Okay, so the third question, which is a little bit more tricky. So here, by the way, we're using the same matrices A and B. So A in this case is 1, 3, 5, 1, and B in this case is 1, 4, 1, 0. Okay. And the question is, can you find constants C and D where if you add CA and DB, you're going to get this other matrix 2, 7, 5, 1. Okay, so this is a little bit tricky. So maybe I'll give a hint. So, well, what we want is CA plus DB equals 2, 7, 5, 1. So the first question is, what would C have to be? And my hint is, look at the fourth entry. So if we want to take some multiple of A and add it to some multiple of B and end up with this matrix over here, then what would we need as the coefficient on A here?
Yes. Can I come
Yes. Yeah, Ed?
in? Can I come in?
Yeah, Ed?
Yeah, okay.
Yeah.
So what I did, to solve that problem,
Mhm.
I put them in equation form. That is,
Mhm.
since I have CA plus DB, I look at the first metric, which is 1 in the first row. The first column is 1.
Mhm.
So I consider that to be, I said that C plus D will be equal to 2 in my first equation.
Great.
Yes. Then my second equation on the second row, on the same first row, 5C plus D equal to 5.
Great.
Then I go to the second row, in the second column, 3C plus 4D equal to 7.
Great. So 3C plus 4D equals 7.
Then the last one, I get C plus 0D equal to 1. So that's simplified as C is equal to 1.
Great. So that means C
So
equals 1. That's fantastic. So now that we know that C is equal to 1, what else do we know?
And I substituted the value of C equal to 1
Right.
in all the equations over there.
Okay, so if we substitute them all, then we get 1 plus D equals 2, 5 plus D equals 5, and 3 plus 4D equals 7. Right, so we're substituting C equals 1 in everything. Great. And so what happens
then,
now?
And then we found out that, I found out that 5, this equation, 5 plus D is not equal to 5. But all
Right.
the other ones satisfy equation C is equal to 1.
Right. So exactly, right? This gives us that D is equal to 1 from the first and the third equations, and D has to be equal to 0 from the second equation, right? And so this is impossible. Right, so yeah, so that's a great solution, right? D equals 1 and D equals 0. First and second equations, impossible to have both, right? So that means that there is no solution, right? Because you would have to simultaneously have D equal to 1 and D equal to 0. And we know that we can't have that. Okay, so I'll just write it in red. So the answer is not possible. Okay, great solution. Okay, any questions on this? Let me,
Hello?
Hello, yes? Sorry, just unmute yourself. I just needed to get the background. Tomas, you can ask your question.
Yeah, I could not understand. I would like you to go through it, please.
Okay. So from the beginning here. So what we're doing, right. So we have this equation, CA plus DB equals 2751. So that looks like one equation, right? But it's really 4 different equations, right? Because it's an equation in each position, right? Let me put it on a new sheet, right? So what we're really asking is C times 1351 plus D times 1410 equals 2751. So what we really have is a different equation. So I could write this out, for instance, as I could multiply in the C and the D. So that's C, 3C, 5C, C, plus D, 4D, D, 0 equals 2751. Right? Are you with me still?
Yeah.
Right. And so now we get a different equation for each position. So for the top left, we get the equation C plus D equals 2. And then for the bottom left, we get 5C plus D equals 5. And then the top right, we get 3C plus 4D equals 7. And then for the bottom right, we get C plus 0 equals 1. Right? Because we get an equation for each position in the matrix. So it's 4 equations in 2 variables, right? When you have 4 equations in 2 variables, usually you do not get any solution. And in this case, that's right, because this equation over here, C plus 0 equals 1, definitely gives us that C equals 1, right? That's the only solution. So now we substitute, this becomes 1, this becomes 5, and this becomes 3. Right, this is substitute C equals 1. And what we end up with is 1 plus D equals 2, 5 plus D equals 5, 3 plus 4D equals 7, and 1 plus 0 equals 1. Now, 1 plus 0 is equal to 1, so we don't have to worry about that. But these equations, these 3 equations together, these cannot be solved for D. Right? Because you get that D equals 1 in one of the equations and that D equals 0 in the other equations. Okay? Is that clearer?
Yeah, I'm following.
Okay. Great. Other questions?
Yeah, bro, Andrew.
Yes.
The Prince. So they are looking at the power and looking at this. For every case you are asked to find D, is it possible that D can be found here?
Right. But you need one D that works for all of the cases together. And there's no one D that's going to work. Because for this one, you need D equals 1, but here you need D equals 1, but here you need D equals 0. So there's no one choice that will work for all the cases together. And so that's the problem. So that's why it's not possible.
Okay, thank you.
Right, you're welcome. Other questions? Okay, so let's move on. Okay, so this is just the basics of matrices, but we basically went over all of this already. So a matrix is a rectangular array of real numbers. If we have 2 matrices of the same size, we can add and subtract them by adding and subtracting the entries. And if I have a matrix and I have a real number, then I can multiply the real number by the matrix, and I get this new matrix, which is the same as the old matrix, but every entry is multiplied by this number. Okay? So this, we really did all of this already. So maybe there's no point in going over it because we did it all in the homework questions. What I want to talk about today is more advanced operations on matrices. So again, if you took the class last spring, then you've seen all of today's material. But next week, we'll get into new things. If you haven't done it, then maybe this is new. And even if you did see class last year, then it's maybe nice to see it again. Okay, so what I want to talk about is multiplying matrices. Okay, so we've learned how to add 2 matrices, and we've learned how to subtract 2 matrices. And now what we want to do is multiply 2 matrices. So I could try to make a definition over here by saying, okay, I have 2 matrices of the same size. What's their product? Well, their product is going to be I multiply the entries position by position. And I could make that definition, but it turns out that that definition is actually just not that useful. And instead, we're going to define a a weird multiplication where if I take an m by n matrix and I multiply it by an n by p matrix, then the result is going to be an m by p matrix. Okay, so for instance, if I take a 2 by 3 matrix and I multiply it by a 3 by 1 matrix, then the result is going to be a 2 by 1 matrix, right? Kind of what you need is these 3s to match. The number of columns of the first matrix has to equal the number of rows of the second matrix. And then once those match, what's the dimension of the results? Well, you cross out the matching 3s, and what you're left with is a 2 by 1 matrix. Okay, so this is going to govern the sizes of the matrix that we can multiply. If you want to multiply them, you have to have that the number of columns of the first equals the number of rows of the second, and then the result will have number of rows same as the first matrix and number of columns same as the second matrix. Okay. And if you don't have this, then we just say that multiplication is undefined. We just say we cannot multiply the matrices. So if I have a 2 by 2 matrix and I want to multiply it by a 3 by 3 matrix, we cannot do that. Okay, we just say it's undefined. Okay. So what we're going to see on the next slide is how do we multiply matrices? Okay. And the definition may look a little weird and a little unmotivated, but hopefully throughout this course, throughout this semester, I can convince you that it's a good definition and it's the right way to do things. Okay, so let's look at what the actual definition is, what the formula is. Okay, so let's try to do this with an example. Let's say that I want to do 1, 2, 3, 4, and I want to multiply it by 1, 2, 3, 4, 5, 6. Okay, so what I'm going to do is I'm going to write them. Oh, I'm going to write them like this. Oh, let me do blue. Okay, so I'm going to write them like this. So I have 1, 2, 3, 4. And then here I'm going to write this matrix 1, 2, 3, 4, 5, 6. But I'm going to write it very big so that I have enough space to do everything. So I'm going to write this matrix very big and I'm going to write it up and to the right. And the product, which I'm going to put in red, is going to fit here. Remember, first of all, that this is a 2 by 2 matrix times a 2 by 3 matrix. And that's okay because this 2 matches this 2. So that means the final dimension, I can cross out the 2s and I'm going to be left with a 2 by 3 matrix. So whatever I write down here, this is the product matrix. Is going to be a 2 by 3 matrix. So it turns out, what do I do here? Well, to get each entry in this matrix, I'm going to multiply the corresponding row of the first matrix by the corresponding column of the second matrix. Okay? And what does it mean to multiply a row by a column? Well, what I'm going to do is the dot product on vectors, right? This row is a vector 1, 2. And this column is a vector 1, 4, and so I'm going to take the dot product. So what I get in the first entry is 1 times 1 plus 2 times 4, right? I'm taking the dot product of 1, 2 with 2, 4, so I have 1 times 1 plus 2 times 4. In the next entry, I'm going to do 1 times 2 plus 2 times 5, and in the last entry, I'm going to do 1 times 3 plus 2 times 6. Right, in both cases, I'm taking a dot product of this row and doing the dot product with the appropriate column. Right, so here I have 1, 4, here I have 2, 5, and here I have 3, 6. Right, so 1, 1, 2, 4, 1, 2, and 2, 5, and 1, 3, and 2, 6. And then I can do something similar on the bottom row. To get the entry on the left, I'm going to be doing the dot product of 3, 4 with 1, 4. So I get 3 times 1 plus 4 times 4. And then over here, I do 3, 4 with 2, 5. So I get 3 times 2 plus 4 times 5. And then over here, I do 3 times 3 plus 4 times 6. Okay, and so if I need to simplify everything, 1 times 1 plus 2 times 4 is 9. 1 times 2 plus 2 times 5 is 12. 1 times 3 plus 2 times 6 is 15. 3 times 1 plus 4 times 4 is 19. 3 times 2 plus 4 times 5 is 26. And 3 times 3 plus 4 times 6 is 33. Okay, so this is the answer. If I take the matrix 1, 2, 3, 4, and I multiply it by 1, 2, 3, 4, 5, 6, the answer is 9, 12, 15, 19, 26, 33. Okay. So it is this strange thing where each entry of the product matrix is actually a dot product of two vectors, right? It's going to be a dot product of the entry from the appropriate row of the first matrix and the appropriate column of the second matrix. So I'll give a real definition on the next slide, but before I go on to that, is this clear, or do you want me to talk a little bit more about any part of this definition or how I did things?
Yes, bro, Andrew.
Yes. Princeton.
My question about due to the multiplication of the matrix. We see we multiply 1 by 1, which is 1 times 1.
Mhm.
But I see the plus that between here. How can we call the plus here? So if we are multiplying the row by the column, we should use a plus between it to add.
Right. So because the point is that we're doing dot product, right? So the reason we have the plus, so y is plus, well, the point is that we're doing the dot product. So what we're doing here is the dot product of the vector 1, 2 dotted with the vector 1, 4, right? Because it's the dot product of the first row here and the first column here, right? So we have 1, 2 dotted with 1, 4, and remember how the dot product is defined. You take the product of the first entries of the vector, and then you add the product of the second entries in the vector, right? So the reason there's a plus is because that's part of the definition of the dot product, right? The dot product combines addition and multiplication. And so when we do matrix multiplication, it's based on the dot product. And so there's always going to be a plus there in every term. Is that okay? Is that clear? Okay.
Yeah, thank you.
You're welcome. Other questions? Okay, so let me actually give you a definition, right? I mean, I gave this example, but let me give you the actual definition. So suppose that A is an m by n matrix and B is an n by p matrix, then the product matrix, which we write AB, so I already said on the earlier slide, it's an m by p matrix. And well, what do we have? So it's a lot of letters, so it can kind of make your head spin. This is why I wanted to do an example before I gave the definition. But the jth entry in the ith row is given by taking the dot product of the ith row of A and the jth column of B. So that's a mouthful, but let me just draw a picture of what this means, right? Let's say I have my matrix A, who knows what size it is, and then I have my matrix B over here. And so let's say that I write the rows of A as vectors. So I'm going to call this V1, V2, and all the way down to, well, A has M rows, so it's going to be VM. And now B is going to have P columns, so I'm going to write its columns as vectors. So you can think of the column, the first column of B as being some vector, we'll call it W1, and then W2 and W3, all the way up to WP, right? Because B has P columns. And now I'm going to find my new matrix. And what are the entries in this matrix? Well, it starts with V1 dotted W1, and then V1 dotted with W2, V1 dotted with W3, and so on, all the way to V1 dotted with WP. In the next row, we have V2 dotted with W1, and then V2 dotted with W2, V2 dotted with W3, and so on all the way up to V2 dotted with WP. Sorry if the writing's a little small. And then this continues all the way down the matrix. And in the last row, we have VM dotted with W1, VM dotted with W2, VM dotted with W3, and then all the way so on. The last one is VM dotted with WP. Okay, so this is maybe a visual definition. Visual definition of matrix multiplication. Okay, and maybe even to make it a little better, I'm going to write these lines down here. I'm going to write the lines for the columns all here. And then I have the lines for the rows. Oops, let me try to write a nicer line. Something like that. The risk of cluttering this diagram a little too much. This is what we have, right? So for each entry of our new matrix AB that I'm going to write down, then this is exactly what we're going to have. We have these entries in each place. So every single entry is a dot product. So multiplying matrices can take a long time if the matrices are big, because you have to take dot products of vectors to figure out every single entry. So it takes much longer than multiplying two numbers. Okay. But this is the definition, and for reasons we'll see, not today, but hopefully by the end of the semester, that there is a point to defining multiplication this way. It's not just so that people can make up complicated formulas. There's a reason you wanna multiply things this way. Okay, and on the homework, you'll get some practice doing matrix multiplication. But so before that, are there any questions about this definition here? You can think of it as kind of like a dot product multiplication table, like a times table. That's what this gives you. It's like you have a times table with the V's over here, the rows of A over here, and the columns of B over here. And then the matrix product is kind of like a times table of all of them using the dot product. Okay, so if that's okay, let's move on. Okay, so there's a special matrix that I want to talk about called the identity matrix. And usually we use the notation IN. So this is the identity matrix that has ones down the diagonal and zeros everywhere else. So for instance, just to write examples, I1 is just the 1 by 1 matrix 1. I2 is going to be a 2 by 2 matrix 1, 0, 0, 1. And then I3 is going to be a 3 by 3 matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Right, so, and I'll write one more, I4 is going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Right, so each one, and you have this for every size. And the point is the ones, you have the ones down the diagonal from the upper left to the lower right. And then every other entry is a 0. Okay, so this is a special matrix called the identity matrix. It's the size n identity matrix. And we have it for 4, but you could do it for 5 and 6, whatever you want. Okay, and so it has this special property, right? So why do we call this the identity matrix? Well, you know from multiplication of just standard numbers that we call 1 the multiplicative identity. What does that mean? It means that anytime we multiply a number by 1, we get the same number back. Right? That's 1 is the multiplicative identity. Okay. So the identity matrix is going to play this same role, but for matrices instead of numbers. Okay. So in fact, it has this property here that if I take the identity matrix n by n, and I take any other n by n matrix, and by the way, remember that if I multiply two n by n matrices together, two square matrices of the same size, the result is another matrix of the same size. It's still n by n. And so it has this property that if I take in times a, or a times in, in both cases, I just get a back. So the idea here is that in is playing the role of 1 for matrix multiplication. Okay. And so let's verify this. I'm not going to do a formal proof of this, but let's just verify this in an example. Let's say that I take 1, 0, 0, 1, and I try to multiply it by the matrix, 2, 7, 3, 6. Okay. Let's see what happens here. Well, what do I have? So notice I wrote these matrices next to each other. So it's a nice little crutch to write the matrix here as if it's an exponent. It helps make the definition clear. But as we do more practice, we're going to just write the matrices next to each other and try to do the dot products in the correct way. So what do we have here for the product? The top entry is going to be 1 times 2 plus 0 times 3. The next entry is going to be 1 times 7 plus 0 times 6. The next entry here is going to be 0 times 2 plus 1 times 3. And the last entry is going to be 0 times 7 plus 1 times 6. Right? I mean, just as an example for this entry, right? Since it's the bottom left, it's going to be the bottom row of the first matrix dot product, the left column of the second matrix. So that's 0, 1, dot 2, 3. And so that's 0 times 2 plus 1 times 3. And if you see what happens when you write this all out, well, lots of these terms have zeros, so we can just delete them. And then the other terms all involve just 1 times something, right? So 1 times 2 is the same as 2. 1 times 7 is the same as 7. 1 times 3 is the same as 3. And 1 times 6 is the same as 6. And so what you see you finish up with here is just 2, 7, 3, 6, right? Which is exactly what we started with. The entries that survive all of these multiplications are exactly the same entries that we had in this matrix to begin with. Okay, so if I take this identity matrix here, right, remember this is called I2, and if this is just some random matrix that we call A, then the product we see I2 times A is just equal to A again. Right, so we verified this formula for these matrices. And I encourage you to play around with this a little bit and convince yourself that it doesn't matter that I use the matrix 2, 7, 3, 6, that if I put any 2 by 2 matrix here at all, I would still get this property, that I would get the same matrix back. And then you can also experiment if you do this in the other direction. If I did 2, 7, 3, 6 times 1, 0, 0, 1, that I would also just get 2, 7, 3, 6 back. And if you want to do a little practice, you can try to do this with a 3 by 3 matrix. Try to take I3, 1, 0, 0, 0, 1, 0, 0, 0, 1, and write down just some 3 by 3 matrix and multiply them together and show that when you multiply them together, you end up getting the same matrix. If you multiply I3 by some matrix A, that you end up getting A. Okay, so this IN matrix plays the role of the multiplicative identity. It means that if you multiply it by any matrix, you get the same matrix back. All right, are there any questions on this?
Yes, I think I have a question, observation.
Yes, Ed?
Yeah, so there's a clear indication that the identity matrix can only be multiplied. If it is 2 by 2, it will be multiplied by 2 by 2 matrix. It cannot be multiplied by 3 by 2 dimension matrix, right?
Well, so that's a good question, right? So let me write this on a new page. So if I have the identity matrix, right, I2, so this is a 2 by 2 matrix. So right now I'm just multiplying it by 2 by 2 matrices, but in fact, I can do a 2 by 2 matrix times, I can multiply it by a 2 by P matrix for any P, right? If this is a 2 by 2, I can multiply it by a 2 by P matrix for any P, and the result is going to be a 2 by P matrix. So in fact, we have that I2 times A is equal to A for any 2 by P matrix A. Yeah, so the A doesn't have to be a square, but it does have to have exactly two rows in order to make it work. And similarly, if I take A times I2, this is going to be equal to A for any M by 2 matrix A. Right? Because if this thing is M by 2 and I2 is 2 by 2, then their product is going to be M by 2. So it's going to be the same size. And in fact, if you use the identity matrix, you're going to get A back. So if you're going on the right, if A is on the right, it has to be 2 by P. If A is on the left, it has to be M by 2 or P by 2. It doesn't matter what letter you use. And if A happens to be 2 by 2, then you can do it on either side. Okay, so then it's fine either way.
Yeah, okay.
Does that answer your question, Ed?
Yes, thanks.
Okay, great, you're welcome. Rufus?
Okay. Yes. Yeah, what I learned from this explanation is that once the matrix is a square matrix, it is applicable to find the product. And then the next one, if the number of rows of the first matrix correspond with the number of columns of the second matrix, it means it is applicable.
Exactly. Correct.
Okay. Thank you.
Good. You're welcome. Any other questions? Okay, so let's do one more slide. I want to see, what do we have? A inverse. Okay. All right. So when we have the identity, anytime you have an identity element, you can ask about inverses. So remember in just the real numbers, right, that if we have a real number that's not equal to 0, then we call it A, and we can always take its reciprocal. That's called 1 over A. And we sometimes call that the multiplicative inverse of A. And why do we call it the multiplicative inverse? Well, it's because if we take A and we multiply it by 1 over A, and of course, it doesn't matter which order we do it in, right? A times 1 over A is the same thing as 1 over A times A. In either order, we get 1. And this 1 here is the multiplicative identity. Okay. Right, so this 1 is the multiplicative identity. Okay, so what I want to do is make the same definition, but for matrices instead. So let's say, so for now, we're going to have a square n by n matrix. So let's say that I have another n by n matrix that has the following property. So if I'm given A and I have some other matrix B that has the property that AB times E, that AB and BA themselves are both equal to IN, both equal to this identity matrix, then what we say is that B is the multiplicative inverse of A. And as a matter of notation, we write that B equals A to the minus 1. This is the notation that we use. Okay, so we see, right, this is exactly the matrix analog of what we have with numbers. What does it mean that two things are inverses of each other? It means that we multiply to the identity. So just like in real numbers, 3 and 1/3 are multiplicative inverses. Why? Because they multiply to 1, which is the identity. So we have the same thing with matrices. If A and B are multiplicative inverses, that means they multiply to the identity, and you can also do it in either order, right? AB and BA both have to be equal to the identity. Okay. And so the question is, how do we calculate this? And in general, this is somewhat complicated, but I'll show you a couple of special cases. So we're almost out of time, but let me give you one last formula before we end. So how do we calculate this? Okay, and well, I'm going to give you the formula for 1 by 1 and for 2 by 2 matrices. So if I have a 1 by 1 matrix, which means it's just a number, then its multiplicative inverse is just a 1 by 1 matrix that has the reciprocal of that number in there. And that's because if I take the matrix A and I multiply it by the matrix A inverse using 1-by-1 matrix multiplication, this is just A times A inverse, which we know is going to be 1. And this is the matrix 1 is the 1-by-1 identity matrix. Okay. So this is fine. And you can do it in the other order also, right? A inverse times A is going to be A inverse times A, which is the same thing as 1, which is the identity matrix. Okay, so a 1-by-1 matrix is relatively easy. So to invert it, you just invert the number inside the matrix. You take its reciprocal. Okay. All right, so the last thing that I want to say today is the 2-by-2 matrix, because you're going to need to know this to do the homework. So if I have a general 2-by-2 matrix, I just call the entries A, B, C, D, then its inverse is given by this kind of strange formula. So you take this scalar on the outside, you take 1 divided by AD minus BC. So we'll talk a little bit more next time about where this comes from. But for now, it's just a formula. So 1 divided by AD minus BC, and we multiply it by this matrix that looks like a shuffled version of A. It's DA and minus B and minus C. So the way you remember this is that you switch the A and the D, and then you negate the B and the C. Okay, so it turns out that this is the formula for A inverse, and this formula always works except, well, you have a fraction here and you have a denominator, right? So you don't want to be dividing by 0. Then the function doesn't make any sense, right? The formula doesn't make sense if you divide by 0. Okay, so this is okay as long as AD minus BC is not equal to 0, right? You need AD minus BC not to be equal to 0. So I'm sorry, I know we're over time, but let's just go 3 more minutes just because I want to do one example. So I think that'll make this clearer. So if we wanted to find the inverse of 3, 2, 1, 1, let me actually just do it on the next page, on the previous page, so you can see the formula. So let's suppose that A, so as an example, let's say that A equals 3, 2, 1, 1. Well, then A inverse is going to be equal to, well, I have to take 1 over, well, AD minus BC. So that's 3, 1 minus 2, 1. So 3 times 1 minus 2 times 1. And then I'm going to multiply it by this matrix where I switch the 3 and the 1. I switch the 3 and the 1. So that gives me a 1 and a 3. And then I negate this 2 and this 1. So I have minus 2 and minus 1. And what is that? Well, 3 times 1 minus 2 times 1 is just 1. So that's 1 over 1 times 1 minus 2 minus 1, 3. And this is just 1 minus 2 minus 1, 3. Okay, so this is the inverse. And what you should check, maybe I won't check it now, but this is a good exercise. Check that if you multiply A by A inverse, or if you do A inverse times A, check that you get the 2-by-2 identity in both cases. Okay, so A is this matrix 3, 2, 1, 1. A inverse is this matrix 1 minus 2 minus 1, 3. And it's a good exercise to check on your own that if you multiply them together, and it doesn't matter which order you do them in, you can put either one first or either one second. If you multiply them together, then you will end up getting the 2-by-2 identity. Okay, so this is a good exercise to check. And so let me just say this is just the problem over here. So I'll just say see previous slide. And then, so there's a couple of homework problems that we have. So this is just some matrix multiplication. I ask you to compute AB and BA, and I ask you if they're the same. Then here is a matrix inverse to compute. And then here I have a matrix A and a matrix B, and I tell you to verify that if you multiply them together, you get the 2-by-2 identity. And then the question is, are these two matrices inverses? Why or why not? Okay, so those are the exercises for the week. And next week, I got the date wrong on this, next week on November 11th. So we're going to discuss how matrices interact with vectors. So we're going to review some of this inverse stuff because it went a little fast. And we're going to discuss how matrices and vectors interact. And they do things called linear transformations. And this is going to involve lots of geometric things like rotations and reflections and dilations and things like this. Okay, so thank you again for your attention. And I hope you have a great weekend. And we'll stop here with the new material. Are there any questions?
Sure.
Okay, there's no questions. Sange, do you need to say anything?